This is the video for the Newton's third law test that you have just recently done. You should have a copy of the paper, but if you don't, here's question 1. What we got a train with a total mass of 80,000 kilograms, and it consists of an engine, labelled as E, and 2 trucks, A and B. And we're not given the masses of the engine or the carriages. Now the resistance to motion on the engine is 10,500 newtons, and then there's a resistance of motion for both of the carriages, and that's indicated by a line above the diagram. We're told that the couplings are light, so we don't have to worry about the mass of the couplings, X and Y, and we're also told that they're horizontal, all the forces are acting horizontally. The train is moving along a straight horizontal track, and okay, so everything is given to us on those words is also given to us on the diagram. And that's often the case. Now if that diagram wasn't given to us, then we could have quickly drawn a diagram, not with an engine but with particles, just to try and understand the paragraph that we were given. But that's not the diagram that I recommend that you use to solve the problem, or begin to solve the problem. What you need to do is you need to think about zooming in and out. Now in lessons I likened it to the idea of Google Earth. Google Earth, you can zoom right out and see the planet, you can zoom in to see England, you can zoom in to see Somerset, or you can zoom in to see even your house and your back garden. So what we have to do is we have to zoom in on the appropriate part of the model and then consider the forces on those models. Because using Newton's third law, we know that any connected forces, like the couplings in X, are equal and opposite, and the couplings in Y are equal and opposite. And also, as these are connected particles, then if this engine's accelerating with an acceleration of A, so is this carriage, and so is this carriage. And if this engine's travelling at speed v, or velocity v, then so is this carriage, and so is this carriage. So there's common unknowns in this problem. So the first part of the problem is to model, and it's actually told us by modelling the whole train as a single particle. So it's given the hint that we should be zooming out and considering this model as one particle. We need to show that it is decelerating when the driving force of the engine is less than 15,000 newtons. Okay, so that's part 1. So what I'm going to do for this part 1, and this is what I recommend you do for all mechanics questions, is draw a quick diagram, a quick model of the situation. Now here's the train, but here's the train and the carriages. Now that's the important thing, the train and the carriages. And we've got to find the driving force for which the acceleration A on this diagram is negative or less than 0. Now the forces opposing motion are 10,500, 3,000 and 1,500. Now you can show them as one single force if you like, and then sum them, or you can identify them as separate forces on the diagram. Now the mass of this particle is 80,000 kilograms. Although we're not given the individual masses of the engine and the carriages, then we are given the mass of the entire train. So there's our quick model, and what we've got to find is driving force when the acceleration is less than 0. So let's find when the acceleration is equal to 0. So let's resolve horizontally, setting that direction to be positive, and we're going to find driving force when A is equal to 0. So I'd like you to pause the video and resolve the forces yourself now. Okay, we should have resolved the forces. Now anything acting in this direction is positive and anything acting in this direction is negative. So we get FD minus 10,500 minus 3,000 and minus 1,500 is equal to the mass times by acceleration, which in this case is 0. So FD is equal to if you add those up, you get 15,000 newtons when A is equal to 0. So for A to be less than 0, the driving force has to be less than 15,000 newtons. And remember, A being less than 0 is the deceleration that we were looking for. So this is decelerating when A is less than 0 if we're taking the right direction to be positive. So that's the first part of the question. Part II, or 2, is show that when the magnitude of the driving force is 35,000 newtons, the acceleration of the train is 0.25 meters per second squared. So we've got to show that acceleration. But what's good is they've actually given that acceleration, so if you couldn't have done the first two parts, you can still use that acceleration for future parts. But, right, and also it's a nice feeling in exam when you've actually shown the figure that you've been asked for. So we have now got this driving force, which I've got on this diagram as 35,000 newtons. So now if I resolve again, I get 35,000 minus 15,000 equals 80,000 A. Remembering this is F equals MA because I've resolved horizontally, taking right to be positive. So the driving force is 35,000 newtons. We worked out in the first part that the resistive force is 15,000 newtons. So now we just have to solve the equation for A. So we get A is 35,000 divided by 15,000 all over 80,000. 80,000 is the mass, which turns out to be a quarter meters per second to the minus 2 as we were asked. So we have shown that A equals 0.25 meters per second minus 2. Box up your answers so that they're easy to find. So that's part II. Now the third part is hence find the mass of E given that the tension in the coupling is 8,500 newtons when the magnitude of the driving force is 35,000 newtons. So what we're now doing is we're considering E. In this model here, we're now not considering the entire train as a whole, so we haven't zoomed out to look at as a train as a single particle. We're now going to zoom in and consider this train. But we will have to consider the coupling force, X, which we have been given. So what I'd like you to do now is draw the third part, draw a new model, but just consider the engine at the front, please. Pause the video. Well, you should have by now been able to draw the engine. Here's the engine, which we can call E. We don't know its mass, but we do know there's a driving force here of 35,000 newtons. We know there's a coupling force, which is if this engine is pulling the two carriages in that direction, then the Newton's law say that there's an equal opposite force on the engine in that direction. We know the acceleration in this direction is a quarter, and we were told in the question that that force, that force is 8,500 newtons. So that's the second part now. So there's our model, and hopefully you've drawn something very similar. We don't need the carriages. In fact, we shouldn't have the carriages on at this stage because we're only considering the engine. And Newton's third law tells us the force that we're in the coupling is equal and opposite. So there's also that force acting on the first carriage. Right, now, as usual, we're going to resolve horizontally, taking the right to be positive, and we're going to use F equals MA. So resolve now, and then restart the video when you have done. Right, well, every force acting in that direction is positive, so we get 35,000. Any force acting in this direction is negative, so we're taking away 8,500. And that's going to equal a quarter of m, because the acceleration's an a quarter, so the a is a quarter, and we don't know the mass of the engine, so we're going to call it m. Now remember that the whole train was accelerating at a quarter of a meter per second, so the engine is also accelerating at that rate. So now it's just a case of rearranging to find m. So m is equal to 4 lots of 35,000, take away 8,500, which is 64,000 kilograms. And box up your answers to make it easy for the examiner. Oops, 64,000 kilograms. Now there's some new text, so that often when there's a new text dividing two parts, something has changed in the model. So always think about it carefully and don't try and adapt an earlier diagram, draw another diagram for this situation. Now it says the driving force is replaced by a braking force of magnitude 15,000 newtons acting on the engine. The force accepted by the coupling Y is 0, so on the last carriage B that force is 0. Show that the coupling, find the mass of B. Now you might think, well, there's no force there, how's it slowing down, how's it decelerating? Well, don't forget that there's a natural resistance to motion here of 1,500 newtons. So what this is saying is that when this braking force is applied, it matches the deceleration such that it matches the deceleration that would have been caused just by this force here. But that's not something you really need to worry about. You just need to work through the model and that will become apparent at the time. Now, as that's 0 here, if we know the acceleration of the entire train, then we can find the acceleration of the carriage. Now when I say acceleration in this case, I expect it to be a negative because it's a deceleration. Okay, so I can say acceleration whether it's accelerating or decelerating. So we need to look at the entire train before we worry about carriage B. Now the problem is, if you zoom straight in on carriage B, you won't have enough information to solve the problem. Now if you do it that way around, then you may then say, well, okay, I need something else, so let's look at the entire train in one particle. But with experience, I know to look at the particle first straight off. So what I'd like you to do is draw a new model for the new case for the entire train. And when you have finished that, then you can restart the video. Okay, so there's my model for the first of my models of part 4. It's the entire train, so it's the train, the engine and the two carriages. So as a total they have 15,000 newtons. Now that is the natural resistance to motion that we have here, air resistance and friction probably combined here. But it's also now got the additional braking force defined as 15,000 newtons acting on the engine. Now if it acts on the engine, then it will act on the train as a whole. I've started off setting the acceleration to be in that direction, but as I noticed all the forces were in that direction, I thought, well, I might as well change the acceleration round. It didn't matter. If I kept the acceleration in that direction, when I resolved to find it, I would just get a negative value. And as long as I'm consistent, then the vectors, the mathematics of the vectors, will sort itself out. So we're going to resolve horizontally, and I'm using Newton's second law, F equals ma. So pause the video and restart it when you found acceleration. We got 15,000 plus 15,000 equals 80,000. So A equals 30,000 over 80,000, which is equal to 0.375 meters per second per second. Now it's not an answer that it's not our final answer, but it was well worth boxing up because it's an intermediate answer that an examiner might be looking for in order to give you method marks. Now that we've got the acceleration of the entire train, we can now zoom in on the end carriage B. So new model please, and when you've done the new model for the last carriage, restart the video. So here's my model for the second part of part 4. Notice how I haven't put a force on here for the coupling force, because we were told in the question that that coupling force is 0. We could identify it and then make it equal 0 later, but I thought that I wasn't going to include it in this case. So, quite a common thing we've done so far is resolving horizontally, taking right to be positive, using F equals MA, and I get 15,000 equals 0.375 lots of M, because the A is 0.375, and I could call it M1 because we used M earlier to find the mass of carriage B, or I could call it MB. So mass B, if I call it mass B, is equal to 15,000 divided by the acceleration, which we worked out previous step, and that gives us 40,000 kilograms. So the mass of carriage B is equal to 40,000 kilograms. So we now know the mass of the engine, and we know the mass of carriage B, so we can also work out later on the mass of carriage A. Now for the last part, where we have to show that the coupling X exerts a forward force of magnitude 1,500 newtons on the engine, what I'm going to do is I'm actually going to zoom in on carriage A, work out the force on carriage A in this direction, and then using Newton's third law, know that that is on the engine, it's going to be equal and opposite. So if I find the magnitude of X on A in that direction, I know that it's equal and opposite on the engine in that direction. So, can you please now model particle A, and restart the video when you're ready. So there's my model, there's carriage A. It's got its resistive force of 3,000 newtons, it's got the X which is applied to it on the engine, and we don't know its mass yet, but we do know that its mass is going to be 80,000, take away 64,000, take away 40,000, so 4,000. Did I say 40,000 in the last example? Just want to check that. No, it is 4,000, and that will give us the mass of A, MA. Let's just double check I didn't make a numerical error. Yes, I did. So that's 4,000. Apologies for that. Okay, 4,000 kilograms. Now that's quite interesting, because I knew it couldn't be 40,000, because if you add these two together you get more than 80,000. So rather than delete that error out of the video, I'll leave it in there, because sometimes you can spot little mistakes like that in exams because it doesn't make sense. So I don't know, I either copied it down from a calculator, or I put it incorrectly into my calculator. I should have spotted it earlier, but anyway, that's a indication of when you can spot errors like that. So when you work out the mass of A, you get that the mass is 12,000 kilograms. Okay. So now we know that the mass is 12,000 kilograms, we know the acceleration in that direction, we know 3,000 newtons in that direction, so we can work out X by resolving one more time, resolving horizontally, taking right to be left to be positive, using F equals MA, and then you get 3,000 plus the X is equal to 0.375 lots of 12,000. And then you solve that to find out X. And that is X equals 0.375 lots of 12,000 minus 3,000, which is 1,500 newtons, which is what we wanted. But we've shown it's 1,500 newtons on that direction on the carriage, so what we also need to show now then is that X is in that direction, and it's also equal to 1,500 newtons on the engine due to Newton's third law. And that's the end of the problem. So what I've done there, look, I've shown that the force X is equal and opposite on the engine, and we've worked it out, the magnitude was 15,000 newtons, so it's 15,000 newtons in that direction, as we were asked to show on that last part of the problem. And I set you to Newton's third law so that they understand why I've done it. So here's question 2, a very typical connected particle problem. If I zoom a little bit on the diagram, what we've got is we've got two particles, mass P and Q. One is 0.3 kilograms and one's 0.4 kilograms, and they're connected via a light inextensible string. So light, so we don't have to worry about the mass of the string, and inextensible, so that it doesn't stretch, and it passes over a smooth pulley, which means there's no friction. The system is in motion with the string taut, so that it's in motion, so that the particle's connected. An important thing there, as the string is taut, it means that the tension in the cable is equal and opposite. And also, whatever speed that particle's travelling with, that particle's also travelling with the same speed, because they're connected via a taut cable which doesn't stretch. And what we've got to show is that this A has a downward acceleration of negative 1.4. Now that's not the diagram I want to see you use when you're solving this problem. What I want to see you use is two diagrams next to each other. These are connected particles, and often connected particle questions like this lead to the need to solve a simultaneous equation. So what I'd like you to do is pause your video, and once you've completed the model that I've shown you how to do in class, then restart it. So what we're going to do is we're going to consider the particles in isolation. So we're zooming in on P and we're zooming in on Q. Now they are connected via the same cable, so the same string, so this tension here, T, is the same as this tension here, T. Now we've defined them on the diagram as being equal, so we're going to leave them just as T's. Now that's accelerating down as A, and that's accelerating up with the same A. So that's what's going to connect our equations when we have resolved both of the particles. And so what we're going to do now is we're going to resolve this particle P vertically, and I'm going to take down as positive, because I tend to take the direction of acceleration or of motion as positive, and we're going to resolve this particle vertically, and we're going to take up to be positive. In both cases we're going to use F equals ma. So what I'd like you to do now is resolve both of them and give your answers underneath. So when we resolve this P, this is P and this is Q, when we resolve P down, any forces acting down are positive, any forces acting up are negative. So we're going to get 0.3 g, take away T, is equal to the mass of P, which is 0.3, and we don't know the magnitude of acceleration, so we're going to call it A. And the same thing happens when we multiply Q, but we're going to take up as positive this time. So resolve Q, we're going to take up as positive. So we get T minus 0.4 g is equal to 0.4 A. Now we've got a simultaneous equation here with two unknowns. Don't forget G is known. We've got two unknowns, T and A. So there's all sorts of ways you can solve this, but the easiest way to solve this one is to notice if you add the two equations together, then the T's will sum to make 0. So you get negative 0.1 g is 0.7 A. So let's call that 1 and that 2. And what I've done is I've done 1 plus 2. 0.3 add negative 0.4 is negative 0.1, and 0.3 and 0.4 is 0.7. So I'm left with A is equal to negative 0.1 g divided by 0.7, which if you put that into your calculator, you do get the acceleration we're after, which is negative 1.4 meters per second to the minus 2. So I'm going to put that in a box underneath to make it easier for my examiner. Remember always to include your units. Now the second part is slightly harder, but you've got to consider it. And now actually this is a Suvat equation. It says initially P and Q are at the same horizontal level. P's initial velocity is vertically downwards and has magnitude 2.8. Now assuming that P does not reach the floor and Q does not reach the pulley, so there's nothing to stop the acceleration, There's nothing to stop the motion, so the acceleration is going to stay the same throughout. Find the time taken for p to return to its initial position. So what's happening? P is moving in this direction, but slowing down because it's decelerating. And then it's going to return and move in this direction and accelerate in that direction, because for the entire time the acceleration is up with 1.4, because we've worked it out to be negative 1.4 down, so it's up with 1.4. Now what we're going to do is we're going to draw a little diagram of P for the suvat. And what we're going to do is we're going to say, well, initially the speed down has a velocity down has a magnitude of 2.8. It's accelerating down with a magnitude of negative 1.4. So what I'm going to do is I'm going to now say it's up with a magnitude of 1.4. You can stick with negative 1.4 if you want. And this is the important part on this problem. We're trying to find where it goes down, reaches its lowest point, and then moves back up again until it gets back to the point it started. And that's when s is equal to 0. Because remember, s is not distance in the suvat equations, it's displacement. And you can save yourself a lot of time if you remember that. A lot of students think that s is displacement because they still think of suvat equations as being scalars, but they're not, they're vectors. So be careful. Displacement and distance aren't the same thing. Distance is a scalar, displacement is a vector. So now we know that s equals 0, we can think about our suvat equation. So s equals 0. Let's make up to be positive, because that's the direction of acceleration. Doesn't matter, as long as you are consistent. U equals negative 2.8. V equals, well, we don't know, so we don't mind. A is going to be 1.4 because it's acting up, and T is what we're looking for. So we should realise that what S equals U, ut plus a half at squared. That's the suvat equation we're going to use, and we substitute that carefully with what we know. Well, we know S is 0 because it's there and back. We've gone the displacement is 0. U is a minus 2.8 t plus a half of 1.7. So half of 1.4 t squared. So we've just substituted in our acceleration our initial speed, and we're looking for time and our displacement. And we have to solve that quadratic equation. So solve that quadratic equation, please. And then when you're finished, check your answers. So what we've got here is I've just multiplied in the half and rearranged it slightly, and I factored out the t when we're solving this quadratic equation, because remember there's two solutions. There's t equals 0, which is our initial time, which is what we'd expect, and also the time when 0.7t minus 2.8 is equal to 0, when this bracket is equal to 0, and that was when t 2.8 divided by 0.7, which is 4 seconds. So the two times are t equals 0 and t equals 4 seconds. But it's asked us for the time when it returns to its initial position, not when it starts at its initial position. So we're interested in this case in 4 seconds. So that's the third 3 marks for the second part of question 2. Now that leads us to question 3. And what we've got here is we've got a smooth ring R of weight W newtons is threaded on a light inextensible string. So remember, light, so that we don't have to worry about the mass of the string. Smooth, so there's no friction between the string and the bead, or the ring, sorry. The ends of the string are attached to fixed points A and B, where A is vertically above B, and a horizontal force of magnitude P newtons acts on the ring R. The system is in equilibrium with the string taut, so again it's tight, which means the tension in the string is the same throughout, which will be important later. AR makes an angle alpha with the horizontal. the downward vertical, and BR makes an angle beta with the upward vertical. And again, the diagram is given to us here. Now normally with a paragraph like that you will be given a diagram, but again, if not, you're going to have to try and draw the diagram. It then says, by considering the vertical components of the forces acting on R, show that alpha is less than beta, and it's worth 3 marks. So rather than drawing this diagram, which is given to us in the exam, what I'd like you to do is zoom in on R, draw a diagram including all the forces on R. So start that now then please, and when you're ready, restart your video. So here's my diagram. Here's the ring R. It's got a weight of W newtons acting straight down, P acting horizontally, and then it's got 2 forces T, one acting alpha to the vertical and one acting as beta to the vertical. And I did that by considering on this diagram what you were taught in GCSE, angle facts from GCSE. So you should know these 2 angles are the same and these 2 angles are the same. Now, it gave us a hint of what to do in the question. So what it did say is, by resolving the forces vertically, by considering the vertical components of the force. So what we need to do now is we need to resolve this particle, and we're going to resolve vertically, taking up to be positive. We can use F equals MA. Okay, so what I'd like you to do now is for you to resolve those forces, and when you've done them, then restart your video. Right, anything acting vertically up is positive, anything acting vertically down is 0, and anything horizontally or at right angles to the direction that we're resolving is 0. So this P will have no effect on this model. So what we get is T cos alpha minus T cos beta minus W is equal to 0, because this particle is not accelerating in direction, accelerating in any direction, because it's in equilibrium. So if we rearrange this slightly, what we get is we get T cos alpha is equal to T cos beta plus W. Now this T and this T are the same because this is a smooth string and it's not connected, it's just running freely through it. If it was tied on there, then there's a potential for them to be different, but as it's a smooth string running freely, then the tension throughout that cable is the same. Now that means that if these are equal and the T's are the same, then we can write T cos alpha must be bigger than T cos beta, because T cos beta plus W is the same as T cos alpha. Now if the T's are the same, that means that cos alpha is bigger than cos beta. So I wasn't in view, so I'll just quickly show you again. T cos alpha is equal to T cos beta plus W. But as T cos alpha must be bigger than T cos beta, because these two combined is the same as that, and the weight isn't 0 of the ring, so that means that this must be bigger than this, and now the T's are the same, so we get that cos alpha must be bigger than cos beta. Now the last step is to realise then that alpha must be less than beta, and the way to do that is just to sketch the cos and think about it. If this is cos, and this is theta, this is cos theta here. Now if you're further up this axis, so this here, cos alpha is there, and cos beta is there. Can you see that? So cos alpha is bigger than cos beta, then alpha must be smaller than beta. So hopefully you can see that from that diagram. And there's nothing wrong with doing a quick sketch like that in an exam to explain why, if cos alpha is greater than cos beta, that alpha is less than beta. And that's what you were asked to prove or show, so I'm going to give it one of those. Right, and then goes on and gives you a lot of dimensions. Okay, and then it's rewritten underneath in words. And then it's asking you for the tension. Now I know from experience that once it's given us these dimensions, they've given us these dimensions so that we can work out the angles. So rather than going off now and modelling this particle again, or resolving, I'm going to spend a little bit of time very carefully finding all the angles that I need. So almost as an aside, I'm now drawing the diagram they've given us, and that I'm considering them as triangles A and B. Well, that is 0.4 meters. That's a right angle, and that's 0.24. And then I'm going to consider triangle, that's R. I'm going to consider triangle RB. And again, that's a right angle. That's 0.24, and that's 0.3. Now on my diagram, this is alpha, and on my diagram, this is beta. Right? Now, using trigonometry, I can work out cos alpha, but before I go there, I've got to find the missing sides. Well, that's Pythagoras Theorem. So, using Pythagoras Theorem, work out those two missing sides here and here, please. Once you've done that, restart the video. So I've got 0.32 here, squaring that one, and taking away the square of that and square rooting. And I've got 0.18 here, by squaring that, taking away the square of that, and square rooting. Simple Pythagoras Theorem. Now I can work out that cos alpha is equal to the adjacent divided by the hypotenuse, so it's 0.32 divided by 0.4, which is 0.8. And sine alpha is equal to 0.24 opposite divided by the adjacent, which is 0.6. And on this problem, I get cos beta is equal to 0.18 divided by 0.3, which is 0.6. And I get sine beta is equal to 0.24 divided by 0.3, which is 0.8. Now I'm going to need those later on, but I've worked them out now. They've given us those dimensions so that we can work out the angles. They could have given us alpha and beta, but they didn't, so we just got to get on with it and work out the angles, or the cosine of the angle. We could now find the inverse cos of 0.6 to find beta, but we don't need to, because later on, when we've got cos beta in an equation, we can replace it directly with 0.6 without any inaccuracies. Right, what I'm going to do now is I'm going to draw a new diagram, because we've got a new part, and I just want to make sure that I've realized if anything's changed, but also I want to the diagram could have been a couple of pages earlier, and I want to have it next to my workings when I'm resolving. It doesn't take too long to draw a new diagram, as you can see. Now, it's still an equilibrium, but we are now given that P is 14 newtons, and that's important. And what we're asked for now is, in part A, is the tension in the string. Now, what we're going to do to find the tension in the string is to resolve horizontally using F equals ma, and I'm going to take to the right to be positive, but you can take to the left to be positive. It doesn't matter. The vectors will sort themselves out. So resolve that now then, please, and when you've resolved it, well, see if you can find out t from that, but if not, restart the video when you get stuck. Right, well, if we resolve in this direction, anything in that direction is positive, so we get 14. Anything in that direction, or any component of force in that direction, is negative, so we're going to get the component of the two tensions. T sine alpha minus T sine beta is equal to 0, because remember the A is equal to 0. Now we're trying to find out the tension, so a little bit of rearranging gives us T sine alpha plus T sine beta is equal to 14. Factoring out the T gives us T sine alpha plus sine beta is equal to 14. So T equals 14 divided by sine alpha plus sine beta, which is as far as you would have got if you hadn't realized that they'd given us the dimensions so we can work out sine alpha and sine beta. But we know that sine alpha is equal to 0.6, and we know sine beta is equal to 0.8. So when you do that calculation, you get T is equal to 10 newtons. T is equal to 10 newtons. Okay. Right, now we're going to work out this part B, which is the weight of W. Well, to do that, we're going to resolve vertically this time. And again, it doesn't matter which direction you take as positive. I'm going to take down to be positive, using F equals ma. So can you resolve the problem vertically? And when you're ready, start the video again. So anything acting downwards is positive, so we get W plus T cos beta minus T cos alpha is equal to 0. So W is equal to 10 cos alpha minus 10 cos beta. All I've done is added T cos alpha and subtracted T cos beta to both sides and replaced T with 10. Now cos alpha we worked out earlier as 0.8, so 10 lots of 0.8, take away 10 lots of, we worked out cos beta earlier to be 0.6, so we get the weight to be 2 newtons. So for the last part, what we were asked for was the position of R if P is 0. Well, if P is 0, there's no force in this direction, so it's going to hang vertically below B in the lowest position, in the position of equilibrium, which will be vertically below B. Now if you add together the length of the string, these two together, and you work out the distance between A and B, you find that AB is ½ a meter, the length of the string is 0.7 meters, so this is 1/5 of a meter below B. So R hangs vertically, R is vertically below B, 1/5 of a meter below B. Okay, not a very good sentence, but you can see the point. And then it says state the tension in the string. Well, this R is still being supported by a continuous piece of string which is attached to 2 points. So if we're going to draw this as a force diagram, there are still 2 T's acting vertically up, and it's 2 newtons acting vertically down. So if we resolve vertically, we don't really need to do this, but this is belt and braces, we get 2T equals 2T minus 2 equals 0, because it's not accelerating, so T equals 1 Newton. So there it is, there's the test then. I didn't record the last video because you all did so well on it, I didn't think you needed it. But I think you found timing an issue on this test, that you ran out of time. So with practice, with experience of seeing similar types of questions, then you won't take so long thinking about how to approach them. So hopefully this video you found useful.